Okay, so today I'm going to review a few of the electronic properties of those interfaces of quantum titanate. I will briefly mention some results in the literature, and then I will present to you what we have, especially on the LTO-STO system. Okay, so whatever the type of heterostructure you grow, on quantum titanate, lanthanum titanate, lanthanum gallate, and so on and so forth, this is aluminum, sorry. If you get the dimensional electron gas, most of the case you get also superconducting behavior. So remember, doped quantum titanate itself is a superconductor, and the TC that we get from this type of superconductivity is also on the same range of the quantum titanate TC. Now you have a very nice system. It's a 2D system, and of course we can think, is it a good way of studying the Kosterlitz-Thouless transition? So this is a paper from the Triscon group in Geneva, where they try to analyze the IV characteristics at the transition. And they claim that they can extract a Kosterlitz-Thouless temperature, which is lower than the mean field temperature, and that they also, based on this nonlinear characteristic, IV characteristic, says that it corresponds to the moment of you have the superfluid jump, what you expect at the transition. Well, that's a nice result. If you go into details, it doesn't work that well, especially if you look at the maximum, there is a length scale, which is the size of the sample in the Kosterlitz-Thouless transition for the vortex and anti-vortex inviting. And I mean, these numbers in the experiment doesn't work at all. I mean, it's not at all the size of the sample. So I think this result is quite controversial. And there is a paper by Lara and Fato, for instance, which explains that maybe you can understand those results just in terms of disorder. And of course, I mean, you see the TC is not that sharp, especially here, and therefore it's difficult to define mean field TC, and therefore to know where, if you don't know where the mean field TC, it's difficult to get the distance to the Kosterlitz-Thouless transition. So I think this is, I mean, potentially it's a very interesting system because it's a 2D system, and as you will see in a moment, you can change the superfluid density. So for the first time, you can easily change the superfluid density in a charge superfluid and see the Kosterlitz-Thouless transition in detail. So, but I'm not sure we are in this system already at this point. The second order you can look for is magnetism. This is also in those systems controversial. This is a paper from Brickman and al. In 2007. They observed negative magnetoresistance when they put a modest magnetic field, and they see some kind of magnetic hysteresis. So they say, okay, maybe we have some magnetism in the system that was on lanthanum aluminate on quantum titanate. And they have arguments saying that maybe during this reconstruction I was talking about, in this system you may have some free spin coming from the titanium, and they order, and maybe there is a true magnetism in it. This is still controversial. Remember, depending on the pressure you grow your structure, you can have different behavior. And this has been, for instance, in this paper mentioned and put forward. If you have very, very, very low pressure for grade, you are full of oxygen vacancies, and you see the resistivity of the pressure is very, very low. So this is a regime. In this case, it's really a 3D full conducting quantum titanate substrate. The range where you see superconductivity is this one. I think this is where, for sure, we are in the range where there is a gas at the interface which is very confined. In the case where you can find magnetism, it's a very low number of carriers, usually rather high resistivity, and I'm not sure these kind of results have been completely, I mean the result from Brinkman has been reproduced again, maybe because in this case, this is not the best way to get the clean interfaces. There is also rumors or papers about coexistence of magnetism and superconductivity. For instance, those papers from the Dagan's group in Israel, they measure the magnetoresistance of lanthanum aluminate and tungsten titanate system, and they see out of plane magnetoresistance. This is just due to the thickness of the field, but they also found in plane anisotropy. There is an anisotropy depending on if the magnetic field is parallel or perpendicular to the current. And they said that it could be a kind of smoking gun of magnetism within a type of SD scattering or something. Again, this is not completely understood, and this is also for very low doping materials. And even most recently, people are claiming that you may have coexistence of magnetism and superconductivity in the same samples, which in principle is very interesting. But if you look into the details, again, these are very high pressure ground systems and very homogeneous. I don't think if you make a TM cross-section of those systems, then you can find these very well-defined interfaces I was talking about. So I think it's still an open question if there is also magnetism in the system, but I'm not sure it's completely under control. What is under control is the high mobility gas and the superconductivity. Okay, so the nice thing about this system is that since it's a rather low carrier density to the system, you can put a gate, for instance, a back gate on the substrate and modulate the number of carriers. And that's, of course, it's very interesting for the physics. It's essential for the technology. You can use them to make a transistor, for instance. And what you see here is this has been found in 2008 by the Tuscan group, that you can remove electrons and get a transition to a superconductor to an insulator. And if you add electrons, then the superconducting transition goes up and then down again. The maximum is around 300 milli-K, which again is the TC of tungsten titanate. So it's the same kind of dome you can see just with strong dot tungsten titanate. The resistance has this monotonic decrease with some kink here. So they claim that here there is a quantum critical point, and that when you change the voltage, the number of carriers, therefore you cross this point. And they make an analysis with a funny, I mean, it's a kind of analysis with a funny exponent. Yeah.
You're making this comparison with bulk tungsten titanate. There, the dome, at least what you were showing, is you have a logarithmic axis, and so it's not like something like linear here. So
you're talking, yeah.
Link to it, or
yeah. The point is that, and okay, I have no time to go into details. I can come back to this paper, but again, this is a quite funny experiment to use phase one here, and the question is this gate voltage the correct control parameter? And the answer I think is no, and I will try to explain to you on the basis on our own experiment. So I'm not sure this is not a direct or physical parameter, and therefore of course it's a dome in the linear scale and it goes on the log scale. Okay, this I think I will keep because I won't have time. Because you can use this electric field to write at a nanoscale with an AFM. It's very interesting to make devices. The width is roughly 2 nanometers, and so I have time to into detail here. So for the last part of this talk, I would like to present some results we got on the lanthanum titanate tungsten titanate system. And I think this is an interesting one because lanthanum titanate is a mud insulator. This is the only one in all those perovskites I was talking about grown on tungsten titanate and showing today on tungsten titanate. And as I explained to you yesterday, you can understand whether, I mean, on 8 arguments that you can have charges in this system. So the net temperature of lanthanum titanate is like 120 Kelvin. That means for all the low temperature experiments we're talking about here, we'll talk about here, then in principle, this lanthanum titanate is in the anti-ferromantic state. Okay, I will skip the detail of how the samples are grown in Kanpur in India by the group of the Professor Udani, and so we can have a different type of sample with different type of thickness. This is the unit cells, and 10, 15, so below 5 unit cells there is no conductivity at all. Above 20 or 25 the conductivity is very poor, but this is known because above this thickness the strains are relaxed and there are cracks and stuff like that. So I mean the samples are not good anymore. That's we have for. So these are the first measurements we made. So as I explained to you, it's difficult to trust blindly the Hall effect to give the number of carriers. But if you do it, you find the number I was talking about yesterday. It depends on the sample, and the best samples are around 10 units in our cases. And the mobility is quite modest, but those numbers cannot be taken just for granted because it depends on the history of the system, and I will try to explain to you why.
Excuse me, what does the magnetoresistance look like in those samples?
In a few minutes I'll tell you. Okay, so what we have found here is that in fact those systems are very Fermi-like. They have a Fermi-like behavior. Of course, you wonder what are the electrons? Are they in the lanthanum titanate? Are they in tungsten titanate? I explained to you based on the calculation that probably there are more in the tungsten titanate system. If you analyze, for instance, the A coefficient of this temperature dependence, it's more close to doped tungsten titanate than to doped lanthanum titanate. Okay, so probably the electrons are more in the tungsten titanate. And also, if you put the data we have, I mean the TCs of these, at least these two samples, on the plot I was showing you yesterday of the TC for bulk materials as a function of the doping. This is the log scale right now. Roughly, you are on the same range. Okay. Again, there are a lot of dispersion in this point, even in the original curve. So, what you can say is that probably the electron sits in this constant titanate, and what you see is basically behavior of something within constant titanate.
If it would be conduction in lanthanum titanate, would you expect it to be hole-like?
Also,
what are the sign of hole?
Yeah, but the question is, do we? Yeah, of course.
This definitely.
Yeah.
The first proxy because sign of just said.
Yeah, but I mean, if they are just at the interface and spread out, you can wonder how they spread out, and for sure, I mean, it's always negative charge carrier. Okay, always electron. But I mean, originally, using this system, lanthanum titanate, constant titanate, was interesting to see if we can say something about superconductivity in the neighborhood of a mud insulator. Neighborhood is just a general statement. Okay. It seems that the electrons sit more in the tungsten titanate and not that much in aluminate. Okay. Then since it's a superconductor, you can measure the critical field, and it's a very good method to get the thickness of the gas. In our case, we are sure it's below 10 nanometers. Probably, yeah, I mean, this is an upper bound because this is the limit of the precision of orientation of the samples in the dry field. So the coherence length is like 36 nanometers, and that means it's just a regular conductor, a superconductor, nothing special about it. Okay, now since we can put a gate voltage, we did the same kind of experiment that the Tristan group did and others in the literature. And of course, we also are able to modulate the superconductivity and the resistivity on a large scale when we remove or add electrons. And we can do also very nice phase diagram where you have here the insulator, where there's a negative slope, here the superconducting dome, and then here again, is this a quantum critical point? Can we have evidence of that? If we look closely to the data, we see this. That means in our system, clearly the resistance goes here, down, and then there is a kink at 0 voltage. And DC goes down at exactly the same point. Okay? Now, if we measure the Hall effect, to know the number of carriers, that's kind of strange because when we are going this way with the gate, so of course this is 0, so here we add electrons, so of course the number of electrons is increasing, but then at this very same point, like around 0, it goes down. But you are still putting electron in the system with the capacitor. And if now we measure the capacitor, the capacitance of the system and just integrate, of course we don't have the absolute value, but if we say that, you see, this curvature is exactly the same for the whole number of carriers and for the capacitor. So we can just adjust the absolute value here, and you see it's perfect fit. And therefore here we're still adding electrons, but of course the Hall effect at low field is going down. At the same time, if you measure the mobility again at low field, in this region here in the negative voltage, when you remove electron to 0, it's something very smooth, and then it rises up by a factor of 10 when you put more electrons. We don't put 10 times more electrons in the system with the capacitor. So it's just not a good stuff. Now if we look in temperature, that's interesting because again this is the Hall effect. So this is the capacitance here at low temperature, it's well here, and the Hall effect is going down. But when you increase the temperature, then the Hall effect is becoming completely linear, as you expect for a regular system, and this is the capacitance and the Hall effect. So it's matched exactly. So you know exactly the number of carriers you put in the system. And the mobility again, I mean at high temperature the mobility is completely flat with the gate voltage, but at low temperature it rises up. Clearly there is something strange happening here. So we went to Toulouse to the high field facility to measure what's going on, and we measured the Hall effect. And as you can see here, I mean the Hall effect at 0 voltage or at negative voltage is just linear. Right? There's more stuff here, nothing special. But on positive voltage, there is a clear two slopes behaving. Okay, that means that you have two types of carriers in the system. So you can say, okay, Strausson-Tightness is a multi-carrier system I presented to you. But here you have to think that this is not as simple as this picture because it depends on the voltage. If I remove electrons in the system, I just have one type of carrier, and if I put more electrons, I get two types of carriers. And in fact, it's very simple to analyze this system. And this is, for instance, the number of carriers. In fact, you have. So this is the the Hall effect at low field, I presented to you before, and on this sample. And here, in fact, you have most of the carriers are very low mobility carriers here. The one you have at negative voltage, they keep increasing at positive voltage, so you put more and more carriers. But around zero, what you get, you have less, a lot less, but very mobile carriers. And if you look at the mobility, so this is the total stuff you get. If you get at the mobility, you have a fairly constant mobility at the gate voltage for the massive carriers, but you have increasing mobility very fast and rather linearly when you put positive voltage. So clearly you put light carriers in the system only on the positive voltage. And instead, before making a very complicated analysis in terms of quantum criticality, we just used very simple argument to see what's going on in the system when we put just a gate voltage, a back gate voltage. So as I mentioned to you yesterday, it's important to model the interface. So there are a lot of models in the literature. We made our own models, very simple. So you have just a Schrödinger equation, the Poisson equation here. Of course, we have to use this highly nonlinear and temperature dependence of the dielectric constant of certain tightenage. And then we have also to screen the potential. We put everything together and we compute this system. Of course, we have to choose what kind of carriers we are putting first in the system. So basically, we took the masses from the lowest band of certain tightenage, because if we put numbers, the other band are split higher. So these are the sub-bands due to the confinement. So this is the mass in the direction of the transport, and this is the confinement, the mass here. And this is what we get with the numbers we have experimentally. So we put the number of carriers we have in the system, and then what we find is the following. Of course, we have a curvature of the conduction band, which is quite important here, and therefore the electric field is very high, and therefore the dielectric constant of certain tightenage is fairly flat. So it doesn't, in this nice picture, there is no influence of it. And you have a strong peak of the number of carriers. So we put here the number of carriers convert in 3D here, with a maximum and a small tail. It's a log scale here. And then we have, in this calculation, like a few sub-bands filled here up to the Fermi level here. And then when we remove electrons, what we have is we have a few electrons and only a few sub-bands very deep in the well, which are populated. And if we put a positive voltage at 200 volts here, then of course we extend the gas, and you see we put more and more electrons, but what is very important here is that you extend more and more the gas. And in fact, what's going on is that when you increase the gate voltage, not only you change the number of carriers, but you change the extension of the gas quite a lot. Okay, I won't put my hand in the fire on those calculations in the detail, but I think the basic principles are here. And you can see, for instance, this is the extension of the gas in this model, which is fairly flat here in the negative part and rises up at the positive part. And then here, this is what we got from the number of highly mobile carriers from the Hall effect, which rises up at the same time. And what you see also is that DC goes up at the same time. So maybe it's a naive picture, but what we are, the feeling we have is that when you put electrons in the system, electrostatically you put them further away from the interface, and they are highly mobile because they are not strictly 2D like the one which are within the potential way. So our picture is that it's not, we don't have multiple carriers because we have multiple bands, but we have multiple carriers because we have carriers confined in the well and carriers away from the well. So now you see that Vg is not a direct control parameter of the transition. It makes more, it changes this, especially the system. And so I'm not sure we can make a full analysis of the photon criticality based on Vg. How?
Now we still have some like 10 minutes.
10 minutes? Okay. So I will skip, because the question is why is it around 0? What is special about 0? Because in all the experiments it's about 0. If you look in the literature, you see that there is something special around 0, like minus 25 volts or something. So, okay, so we have an explanation for that, but I don't have time to get into this. And the last part of my talk is about transport and magnetoresistance in those systems. Again, we don't have this sign of hysteresis and stuff like that in our measurement. I mean, there is no sign of magnetism whatsoever. But in fact, you see at low temperature we have always weak, kind of localization before the transition here, the superconducting transition in the region of 10 Kelvin. Of course, since it's a 2D system, you think about just weak localization effects. So if we look carefully, these are 2 decades of temperature from 30 millikelvin to 3 Kelvin, and you see we have a perfect agreement between the data and just the regular localization behavior for the conductivity. The exponent here tells you that the main scattering in elastic scattering process is electron-electron scattering in the 2D dirty limit, which is exactly what you expected. Okay. Yeah, I just mentioned that if you put too much current, you have a saturation. I mentioned this because in some papers people claim there are special stuff here, kind of quantum behavior and so on and so forth. It's just trivial. Now if we put a magnetic field, first of all at high temperature, whatever the gate voltage here, we have a perfect B-square behavior, like the Kosterlitz rule. That means that you have a negative magnetoconductance. This is what you expect for a regular system. I choose 50 Kelvin because, as you remember, about 50 Kelvin roughly, the behavior is conventional in the system. Now if you go at low temperature, like this is 2 Kelvin, and this is the conductance, I mean the variation of the conductance as a function of field up to 4 Teslas, then what you see here is that for negative voltage, you have a positive magnetoresistance. And for positive voltage, you have negative magnetoconductance. This has been already observed by the Tristan group, and also the Dagans group and others. And of course, you think about localization correction. So the localization corrections, it's very, very simple. If you have just only a localization, you have, in fact, with the magnetic field, you are increasing the conductance because you are cutting interferences. In this case, you have positive magnetoresistance. And but if you put spin-orbit in the system, then the things are changing, and you have those two terms in the magnetoconductance, and it makes a negative magnetoconductance. If you only use these two contributions, you're not able to fit correctly the data. It has been done this way in the literature, but I don't think it's, I mean, the number to get, for example, the spin-orbit scattering time is reliable. What we put, we add the B-square law we know we have at high temperature. Okay. And so we have just this A parameter which tells you we take into account the normal corrections, not the localization one. If you do so, then you are able to fit, these are the data and the fit in color, the data for all the temperature and for all the voltages, I mean positive and negative. That means this localization is very efficient, provided you don't forget about the Color's law. This is the field at high temperature for the Color's law itself. So now we have to see what's going on in the system, what is changing so much that the magnetoconductance goes from positive to negative. So we can have this parameter, the spin orbit, which is the inverse of the spin orbit scattering time, and d phi, which is the inverse of the inelastic scattering time. First of all, what you have this color coefficient here, A. What you see is that at high temperature it's something which is constant with the gate voltage. But at low temperature, it rises up. This is not a surprise, because the mobility also is rising. And the Color's law is related to the mobility. So nothing fancy about this fact. That means that it's valid to use this parameter in our field. Now, what about the inelastic scattering time? Okay, we have better data. This is like 5 months ago data. But basically, what you see is that it's roughly constant with the gate voltage. Roughly, I mean, there is more variation. But what more important, of course, I mean, the scattering time is decreasing with temperature as we expect. And if you adjust the invert, I mean, the scattering time as a function of temperature, roughly, it's on the log scale, it's a linear slope. This is exactly what you expect if electron-electron scattering interactions are the most important scattering processes. Now, what about the spin orbit? And so at high temperature, the spin orbit, I mean, it's completely flat, and you don't expect with localization corrections, so forget. But at low temperature, what you see that the tau spin orbit going up and then flattens or maybe goes down. Again, I mean, the gate voltage dependence is rather important. And in these two papers, people have claimed that, in fact, you have two regimes. One where you have the regular spin orbit scattering for localization, that is just the potential scattering from the impurities. And in the other regime here, we have a Rajba type of spin orbit scattering. So, yeah. So what does it mean? If you are in the regular impurity mechanism scattering for the spin orbit, then the number of, I mean, the time, the spin orbit time, the scattering time is proportional to the number of collisions, which is just tau elastic. At least what you expect. But in the case you are in what is called the diagonal parallel mechanism, then the tau spin orbit is inversely proportional to the elastic time. So what does this mechanism come from? It can come from the Rajba effect, which is just a relativistic correction on the carriers. So it's not in the scattering on the impurity, which gives the spin orbit scattering time. It's the fact that since you have an interface, since you have a very high gradient for the potential, actually, in the potential well, so a very high electric field, then you can couple the electric field with the momentum of the electrons and have this type of Rajba. So here I plot tau spin orbit as a function of tau elastic, and for at different voltages. You see at negative voltages, roughly, I mean, again, these are only 3 or 4 points, but the trend is good. I mean, tau spin orbit is going up with tau elastic at negative voltage. Now it's not the case at positive voltage. Now if you plot tau spin orbit as a function of the inverse time, then maybe it's the trend is also the one you expect for the Rajba type of spin orbit carriers. That means that maybe there is one way of seeing this system where, in this case, we have the regular spin orbit mechanism for the scattering. You can see from the localization as usual. And in this region here, maybe we have a Rajba type of scattering, which is very important because if you have a Rajba effect, then you can couple the spin and the movement of the electrons, and therefore get into a spin Hall effect and stuff like that, which may be very, very important for applications. Okay, so there is a rather strong issue here. The point is that we know that in this region we have two types of carriers. So we have to make a complete analysis again with two types of carriers into the localization regime and with the Rajba coupling, which we didn't do up to now, and we are still measuring the samples to be sure about this decrease here and how we can analyze the data, either on the basis of the Rajba coupling or just on the basis of very crude two carriers model. Okay, so as a conclusion, I hope I convinced you that the accurate control of the interfaces on quantum titanate is now very important. And there are a lot of groups around the world which are able to grow very high quality interfaces. The detail of what's going on for the electrons at the interface is still an open question. I mean, still it's very interesting. What is the origin of the gas? What are the orbitals exactly? What is the extension and so on and so forth? Surely superconductivity is seen in the system. If we can make the system clean enough, we have a wonderful knob to tune the superfluid density and look clearly for the Kosterlitz-Thouless transition. We tried in our samples, but again, the transitions are not sharp enough right now to be sure, at least at the scale on our measurements, that we observe the Kosterlitz-Thouless transition in detail. And the magnetism question is open here. The field effect and the phase diagram is potentially very interesting. Once you have understood what's going on especially for the gas, because as I try to convince you that when you put the gate voltage, don't put only electrons in the system, of course, you change it drastically. And remember, I told you that in all the calculation of the orbitals, just at the interface, there is a gradient of the occupancy of the orbitals within the 1 or 2 nanometers. So, I mean, you have two difficulties here. One is, what are exactly the orbitals within the well, and how they extend when you pull out with the gate the gap. You have these multi-carrier properties, which are interesting and maybe interesting also for applications, and this Rajba coupling question, which is still open. Thank you for your attention.
So, I'm taking time for questions.
At what density, you say that at some point you see the onset of new bands. At what density does that happen? What is the value of the density?
When I put the gate voltage, we have different samples with. I don't think the density is exactly the good number, because we have studied up to 4 or 5 samples, and the density is not always the same, the carrier density. But what we observe with the gate voltage is always changing rather strongly around 0. This picture. Okay. Okay, maybe I can try. This is something we are still working on. On this picture, let me see. Yeah. Yesterday I told you the the number of carriers is not always the same within a factor of 2. And you can have the number of carriers at high temperature. When you decrease the temperature, in most of the sample you keep the same, rather same number of the carriers. But for some of them you lose carriers. These are just trapped carriers. Okay. Now you measure the sample and you put a gate voltage. And we have to realize something that when we put a negative voltage, of course, we bend the conduction band. We bend conduction band this direction, okay, and of course in the other direction when you put a positive voltage. Okay. That means that you see in the calculations the system, the Fermi level is always very close to the burn conduction band. And this is probably the case naturally in the system because this is on this plot here. I didn't comment about this part of the plot. This is the first polarization curve, which is very important, and we're still working on that. But you see here, this is the whole effect. So you cool down the sample, okay. And this is whatever the absolute value of the number of carriers. I mean, it can be 10 to the 14 or 1.2, 10 to the 14, or whatever. And then you have completely flat whole number, as if you cannot put more mobile electrons. And then you go back, and afterwards, this is completely reversible. This is not trivial. In most of the papers in the literature, people mention that you have irreversibility and stuff like that. You have to be very careful when you cool down and the way you proceed when you put the gate voltage. Okay? This is why the first number for the carrier density I gave you in our experiments are not reliable, because at this time we were not aware of that. And you can see also the mobility doesn't change. There is just a sudden change here around 0. This is just a rearrangement of the system. And what we think is that, in fact, sorry, where am I? No. Yeah.
Yes.
Yeah. Okay. In fact, when you the system, when you cool down, arranges itself the number of carriers, such as the Fermi level is just at the top here. Then, when you balance too much in this system at the first time, then you cannot put more electrons. They just go back. I mean, go this direction. This is maybe also the reason why nobody is able to close the dome, the superconducting dome. Because people try to put more and more carriers to go beyond this number. But, I mean, there is a limit. I think this is trivial limit here. Okay. Then you reverse, and then you put the electron within the potential well. Everything is stabilized, and then you can have reversible stuff. Okay. So this is completely. I mean, this is obvious electrostatic, but I think this is the case. And we are making right now. I mean, I got the news yesterday. About this process, and we for instance, identify relaxation process which are different in this case and in this one. Clearly, this is because we are putting electrons
in the body.
Yeah, in the body. I mean, they just diffuse far away, and this is a slow process. Otherwise, there is a very weak, very rapid process when these are just reorganization within the interface.
Another question? Actually, I also wanted to ask you one thing. When all this story started, people kind of discussing general things claim that there would be a very big difference if I have contact between two band insulators or band and mode insulators, like SrTiO3 or SrTiO and latinum. But in your story, this actually contact between band and mode insulator somehow just looks like the most nature of this latinum didn't play any role, effectively. Am I right or not? What's important maybe is that you can change balances. If you have tungsten titanate, you can have titanium 4+, but it can accept electrons become 3+. Or vice versa, lung titanate. It starts with titanium 3+, it can become 4+. But other than that, looks like the mode nature and proximity to antiferromagnetism and so on didn't play any role in all this story. Is it true or not?
This is unfortunately true. I mean, our motivation to use this system and not the other one was exactly this one. Since we had, we knew we could have maybe mud physics entering into the game. Okay. Unfortunately, first of all, we were the first to discover superconductivity in this system, so we were very excited because we say yes, superconducting stuff, mud insulator in the neighborhood, that will be next. But at the end of the day, there is no sign of mud physics whatsoever right now. And I think the electrons are mainly in the strontium titanate, and this is and all the conducting materials we have in hands behave exactly the same way that the others when you have a band insulator and a band insulator. I just want also to stress that the people, I mean, I mentioned this phase diagram by Okamoto and Millis, which is very exciting. Platinum titanate, strontium titanate, where you expect.
But for their paper, I think the mode nature of this one titanate also didn't play a role, from what I remember. I had this impression actually that it was essentially same physics as though it's simply two benches.
Yeah, that's right. And also, if there is something new, this is for very, very low thicknesses of lanthanum titanate, and even in their view. Low means below 5 unit cells. And in our case, below 5 unit cells, like for everyone, there is no conductivity at all. So it could be just a material problem. And maybe in a few years, it will change. Yesterday I tried to explain to you that maybe it's more deep, that for some electrostatic or strain reasons, you cannot grow, you cannot get charges in the system for smaller thicknesses. But you're right, I mean, there is no sign of exotic physics up to now. There is one question here. Peter?
Okay.
Can you go back to the diagram from Hans Hildenkamp where the various oxygen pressures are compared? It's back there somewhere.
Yeah.
There we go. Yeah, you passed it. Yeah, yeah. So I'm not working in this field, but I've heard some things which I have a hard time reconciling. And one of them is this picture, which seems to suggest that if you make your samples the way they made them, then you should either get superconductivity or magnetism, depending on the number of oxygen vacancies. Is that the interpretation of this picture I should take away? And if so, how do I reconcile it with recent reports of coexistence of magnetism and superconductivity in the same samples?
Okay. First of all, the raw data here are from Brinkman. Okay, but these mentions here are from this paper from Rinchers. I mean, this is a comment saying that maybe we have a different regime. The belief is that in this case, you have oxygen vacancies probably in the bulk. And there have been people, for instance, I mentioned yesterday this experiment from the Kosterlitz-Thouless group, where they measure with a conducting tip the thickness of the gaps. And they said, okay, it's a few nanometers. But in the first experiment, they found conductivity everywhere.
Right.
Okay.
So very low.
Yeah. It's very low pressure. So this is clear here.
That's fine.
Okay, that's fine. Here, in this regime here, there is probably oxygen vacancy, but certainly not in the bulk. Otherwise, they will just short circuit everything. Okay. So probably, I mean, I cannot just be sure that there is no oxygen vacancy. Now, what is the difference between those people and those people here? I don't think it's clear right now. Maybe it could be the rest of the oxygen vacancies which makes the difference between this here and here. maybe also that in this region here, for instance, if you discuss with Van Magnetism, who makes rather high pressure materials, he is the one who found that there are phase separation between magnetism and superconductivity in this system. Okay, that can be neat. That can be also just garbage. So when you increase the pressure, I'm not sure you are able to get the best interfaces in this range here.
So I shouldn't take this very seriously at present. Is that what
It's
you're
not-
saying?
So just a question about that. I mean, you talk about the magnetism as if it is probably associated with titanium-3.
This is what it is.
I mean, but actually, that seems very surprising at the levels of carrier densities presented by various measurements, simply because the occupation of the 3D orbitals is tiny.
Yeah.
And again, I remark that at least there are proposals
They
at
made
the
a-
moment that actually, you know, one way to make magnetism is, of course, to use oxygen.
It can be the case.
Yeah,
Of course,
so-
of course. And indeed, I don't remember the numbers of the number of carriers here, but it's quite low still. But it's probably in the range of 10 to the 12 to 10 to the 13, or something like that here. Okay, which goes in the favor of very low doping, but still it's rather high doping. I mean, the number of carriers is quite high.
So how many per unit cell?
Yeah.
I mean, I think it's much less than 1%.
Mm-hmm.
And it's strange to empty out a D-band and to find magnetism on the...
On a large scale. Yeah, I put a question mark.
No, I think it's a good question mark to have.
But in a sense, actually, the picture of oxygen, for example, the one which George Zavadski advocates, that would probably give you the other way around, because they argue that it's oxygen vacancies which provide mechanism. But then conduction conductivity should be higher.
Well, I mean, I think they would probably actually have to argue that it's clusters of oxygen vacancies.
Right.
Then it becomes a
Conductivity
much more
should
detailed.
be lower and not higher, because conductivity is oxygen vacancies.
No, but I think the bottom curve, we all agree,
Yeah.
is in some sense very different. Even when you're, I mean, there you really have something which is bulk. When you're dealing with, even with these carrier densities, the point is that they're small, but they're not that small. They're sort of 1%, if put part of the 2D sense.
That's a possibility.
Yeah,
The
yeah.
Virginia distribution of the oxygen vacancies.
Yeah.
I mean, in all this game, we cannot remove completely the oxygen vacancies from the game. The argument for saying that in this range, at least, they don't play the major role is the fact that the terminated TiO3 surface is very important to get the gas. So there is, I mean, these are just oxygen vacancies and defects. We don't see a reason why it should be so different. But maybe there is one.
No, there is a simple reason.
Which
In principle, I mean, you can always argue that an oxygen vacancy is a double donor, and therefore it can provide electrons. It can't provide holes, and so so it's even stabilized by the fact that you naturally produce oxygen vacancies in the vicinity of the TiO interface, because that would be more energetically stable than on the other side. So the point is, it's part of the growth mechanism driven by the polarity of the interface. So I think, I mean, that at least I think is plausible. So you get more oxygen vacancies in the vicinity of that polar interface and not in the other.
Well, we are out of time, so I suppose that we probably just postpone this discussion to the coffee, okay? Okay, let's thank the speaker again. We meet at 11:10.